So, this is lab 4 on spring oscillations. Goal of this lab is to first compare the model prediction for the movement of the spring mass system to the actual movement of the spring mass system. The second, of course, is to verify the energy principle by getting the total energy for the system throughout the entire time period, and hopefully it should sum to 0. So, the result for this lab was, of course, our energy principle is verified, and the model we used to predict the spring motion is quite accurate throughout the entire time period. So, our overall layout for this lab is going to be first, a discussion of the physics, second, a discussion of the computer model, and how it predicts the motion, and how it calculates the energies, and third, the important what does it mean questions. So, the physics. We start off with, of course, our fundamental principles, Newton's second law and the energy principle. So for this specific example, we have the spring force and the gravity force both acting upon our spring mass system, and we have the potential, kinetic, and spring energies to account for in this system. So, the application of this problem. So, the Newton's second law we of course use for predicting the movement of the mass throughout this entire time period. We'll calculate the spring force using Ks times S, and we'll calculate gravity by using negative mg, and we'll add those two vectors together to get the net force, and of course use the formula Vf equals Vi plus F net over m delta t to calculate the new velocity, then calculate the new position from there. And for energy principle, we'll of course take the sum of the potential, kinetic, and spring energies, the formulas which we'll go into later when we're discussing the code, and we'll sum those three together for the total energy of the current system at that time. So, the code. So, of course, we start off with our initial mass, position, velocity, and time according to tracker. And here we start off with some more constants, delta t, small in relation to the total time, our gravity constant, our spring constant, relaxed length of the spring at 0.123 meters, and our L, which is the total length of the spring at that time, L hat, a unit vector in the direction of that spring, and S, the distance by which the spring is stretched at that given time. And of course, so this is where we have to calculate the energies of the spring mass system. In this case, the formula for kinetic is 1/2 mv squared. For potential is mgh, and the spring force, or the spring energy is 1/2 ks times s squared. So those are three formulas for calculating the energy, and we'll do that for each step of the prediction, and hopefully those three will sum to 0 for every single step of that prediction. So here's our calculation loop. So for our total time period, we calculate our new kinetic, potential, and spring energies, calculate the force of gravity, which in this case is constant, of course, at negative mg. Spring force is in the L direction, of course, Ks times S. Calculate our net force, update our velocity using Newton's second law, and update our position. Here we do the same thing as we did earlier, calculate the length of the spring, the unit vector in the L direction, stretch of the spring, and of course we do some other things to help graph it. And here we calculate the new energies for all of our steps, using the same formulas as we did the first time. So, now we have to answer, of course, our what does it mean questions. So, is the energy principle satisfied? This is, of course, our overall goal for the lab to determine this. So, we can see this very clearly by running the Python model. We'll have two graphs here. This first bottom one we'll look at first. So we have our changes in potential energy, kinetic energy, spring energy, and total energy shown here in the red, green, blue, and yellow order. So our total energy is the yellow line here, which of course we can see is constant at 0 throughout the entire time, as it should be, thus satisfying our energy principle. And up here we can see our nice comparison between our actual spring mass system locations and the predicted locations, which we can see are very accurate, but thus being the other part of the goal of this lab. So, Second question is, compare the oscillation times in the x and y direction for the spring. So we can see the oscillations here in both the x and y direction moving along as we go. So they turn out to be different. The x being 1.63 seconds, the y being 1.52 seconds. So why are they different? They're different because the two oscillation times are from two different movements. The x direction comes from the fact that it's moved to the left of the starting point, and the y because it's moving up from the starting point. So we can see we go from here to the starting point, here to up and to the left. So we have movement in both directions, but those two movements are independent of each other and thus giving us different oscillation times. Thank you.